So I thought let's use this hour and a half to make you think about, invite you to think about one of the most compelling topics in Navier-Stokes theory. It started with Leray himself, and it intuitively makes a lot of sense to think about that question. It turns out that it's connected to the very basic energy estimates we take. One more estimate I need to take. The question is something like this. So if you have if I draw the space-time cylinder, so that's the time, that's omega, that's in Rn. Everybody understood this picture? What is this picture? Why it looks like a cylinder? Aha. So now we need to slow down. No, it's not. What I'm doing here is I take the entire the physical domain, right? You visualize it as it's on. It's on now. You can knock the window, then I will know. You'll have to come. Is it on? Yeah. Okay, so think of, let's say it's a 2D domain, right? So that's the omega, and as time evolves, you can actually map a cylinder. If it is a 3D domain, then you have to just visualize that this is R, right, in dimension. And so I want to see how, so this is what is called omega cross 0 to t, right? So this is the space-time cylinder. So you may ask, in this Navier-Stokes theory, we are taking this all kind of weird estimates. Instead of that, if you go and prescribe a very nice, smooth initial data, and then prove these generalized solutions in 3D, it turns out that you can that energy estimate is good enough to prove even in 3D existence. The uniqueness you cannot prove, or maybe if you put some very smooth, you can prove uniqueness, but you cannot prove existence. But these are all L2 functions anyway. L2 derivative is co-integrable, so the difficulty only comes in a set of measure 0, right? So how does that set of measure 0 look like? Is it is the solution not smooth in a big fat domain? There is maybe pieces of domain, or it's just some dots. What is the can you say that outside a particular nasty domain, right? The singular domain, outside it in the space-time cylinder, the solution is nice, right? And also, moreover, if you can identify such a set, how do you characterize it? If that's going to be a set of Lebesgue measure 0, but it's maybe some other measure to characterize. This Hausdorff measure it turns out to be the right measure to characterize this kind of sets. How many of you studied Hausdorff measure? I had to now recall and look up, so therefore I'm going to write it down. Raise your hand. Hausdorff dimension? Little bit. Hausdorff measure? She raised it and other people looked at it. How could you betray us? Huh? Oh, Hausdorff space. No. This is the Hausdorff measure. So special count the measure it when dynamical systems was popular, chaos and so forth. When I was young, everybody talks about Hausdorff measures, and so it turns out that it's actually appear to be a very small set. Some small set in space-time where the solution is not regular. Outside it is well behaved. What can you say about this set, and how is it very sophisticated mathematics to estimate? It turns out that it's not. At least the first the time estimate, time singularity. Space-time is a little bit more sophisticated. The best results, Timam. So in chapter 5, In this way, you can go and read chapter 5 and you will find that amazingly I already provided you the background. And I am going to take the next estimate. That is essentially the estimate that is used, already presented to you by Professor Bartek Potas when he spoke about the saturation of norms and so forth. That estimate I will prove because I felt that maybe you haven't seen the. So that estimate is the key for the first, what is called the time singularity. Then he prove it in half a page, the famous results of Leray and sharpened by. The space-time singularity was, the best results is due to Caffarelli, Kohn, and Nirenberg. Tells you so I will state it in a moment. And so that is a long paper. It was improved by Feng Hua, Lin. Maybe that's a slightly easier paper to read. Anyway, so that's so end of the day, maybe I thought, where do I leave you as far as Navier-Stokes theory is concerned? Maybe I motivate you to go and look at chapter 5, because it's there was a debate about what is turbulence. Leray thought that. How do I know how somebody who is a lot smarter than me how he thought? But he may have hinted that turbulence has something to do with these singularities, right? The turbulence, the unexplained phenomena of space-time vertical structures and chaos can be something to do with, but right now it appears there is probably not something to do with. But if you prove that such a singular set doesn't exist, then that's another statement of the Millennium Prize problem, right? That there's no sets. Anyway, so that's a good motivation. This is actually chapter 5 in Tima. Let's get rid of that. Okay, so that looks like a very scary result. And in fact, this is probably the one of the most famous results in of course, in rigorous theory of fluid mechanics and also in PDE theory. But it's all about taking some PDE estimates. Okay, so let's go back to energy estimate and. Yeah, I need a black one. Maybe I opened the black one, so now it's going to betray on me. So it was pointed out to me very correctly by some of the students that I shouldn't write so I arrived at this point, right? So go back to the energy estimate. You'll be also somewhat surprised that you will get that kind of huge results, well-respected results, but it's based on some very rather elementary estimates. Anyway, so we came to this level. U dot T L2 squared plus 2 nu 0 to T gradient U R L2 squared dr is equal to actually, but let me put it inequality because when you actually go and prove the weak solutions, generalize x0 L2 squared. When you prove the generalized solution, you end up with an inequality, and that's why you leave it like that. I should write a separate statement like sup of T L2 is less than U of, sorry, this is not correct, dot then 0, dot 0 L2. So this is what we arrive at. I cannot put this one supremum here because I have only separate, right? I arrived at this one separately. Everybody understood the point because it was pointed out to me correctly, and I know just that I forgot that if I drop this, yeah, this inequality is true. If I drop this, that inequality is true, and then I go and supremize this, then I can't sum the two and as I put it in the, so it has to be a separate inequality. And we always in Navier-Stokes theory write it as a separate inequality. Otherwise, you want to combine, you want to put a C. Anyway, so you have this 2 and 3D. It turns out that this is good enough to prove uniqueness in 2D, but not in 3D. But what we are going to do is to write the next level of story. So the typical question is that, okay, so this is for initial data in what space? What is the condition on the initial data? What do you want? If you want this inequality to be valid, what do you want on the right hand side? What do you want? You are thinking too much. Don't this thing has to be finite, right? So the initial data is in L2 here, right? Because I want this to be finite. So initial data is L2, means if you write it out, initial data is omega u of x 0 squared dx finite. So it says that the initial energy is finite. Initial energy is being finite doesn't tell you how distorted the velocity field is, right? It just it tells you how fast things are going, but things that may go fast may not have enough distortion in it, right? In the velocity field. Turbulence is often associated with distortion in the velocity field. So you may ask, how about instead of being L2 in initial data, how about if I give you more H1 space, or maybe the Dirichlet norm is finite. So if the initial data is H1 omega, it's better to put actually divergence free. There are some subtle things about being divergence free and not. There's another way to say that is you saw semi-group. This doesn't belong to the domain of a half. It's bigger than. So there are issues like that. But I just say I'm only talking about the norm. What can you say about the corresponding estimates, right? So our key attention, we noticed that this term, what I call the entropy, all of a sudden disappeared on you when I went to Euler's equation. It turns out that that is the term we are always interested in. In fact, if you can show me right here that this term is uniformly bounded in time for 3D, we win the Millennium Prize problem. Actually, you only need L4, you will see. So if you can show that this quantity, not just integrable here, square integrable, but is uniformly bounded in time, right? L infinity in time, then you prove this. So that the whole attention in this, the core of the Navier-Stokes theory is about this Dirichlet integral, and Dirichlet integral is equivalent to H1 norm under what condition? Under what condition?
The H1 0 you have to take, and omega should be with smooth bounded.
Okay, so my question is that when will gradient U L2 equivalence means what? How do you study equivalent norm? You study equivalent norms it will probably come and go unless you see an example, right? So so maybe something like that I want. Some C1, I don't need a C1, U of H1 norm, and then C gradient U norm, right? I like to have this one. What is this guy? What is U of H1 squared is equal to U of L2 squared plus gradient u L2 squared, first derivative and second, the original function are square integrable. Tell me again.
Oh, sorry, omega should be one way bounded. One way it should be bounded.
Yeah, it should be bounded in one direction. And it turns out that you need one of the boundaries, the thing has to vanish. So this is true for all, let's say u belongs to H1 0. Omega. That's certainly true. If omega is a Poincare domain, we discussed that one before, right? Let's still deal with the Poincare domain. You don't need it, but you can. So let's say its domain is either bounded or bounded in one direction. Then you can just by simple integration by parts, you can show that the L2 norm is dominated by the Dirichlet integral, and therefore, first of all, this is a obvious inequality because this has both terms in here. The other one is not obvious because the other one has this term, but not this term, and therefore L2 has to be dominated by that. Okay, so the question is, I put the initial data in. So I, for all the discussion purposes, you are say that I am talking about the Dirichlet integral, right? So what can you say about the evolution of the Dirichlet norm? I'm interested in how this guy evolves in time when the initially it's finite, right? So let's write gradient u dot t. If you want, I can write it out, L2 omega. So let's write it. So this is written as gradient u squared dx, right? So this is squared. Let's write it as, let's say, phi t squared. I may have, did I use phi anywhere before? I have for the initial data, right? So do you want me to use something else? Eta t, right? Eta t. I think Professor Protas used phi. So can I use phi? The initial data phi is forgotten in your mind, right? Okay. So this is some function phi t squared. Why do we do that? So that I don't have to write this clumsy thing every time, right? So I told you that I will give you $1 million. I give you maybe 300,000 bucks if you help me prove that maybe sup t phi t is finite, right? So this is equal to so that is equal to how much is it? 56 crores or equal or whatever you guys do. Whatever. So I claim that proving this one uniformly in time, bounded in time, is equivalent to the Millennium Prize problem, right? In fact, you don't need that. You can actually do better. But let's say that. What does it say? It says that this deformation, or maybe I wrote it as an entropy, right? After integrating, square integrating, I just show me that some way that. I even give you the initial data in that space. If you want, I can give you in a even better space. Take it C infinity in time, in space. Right? 3D. 3D. But we are going to compare 2D and 3D. Right? He's looking for a pen to write. Vignesh, write it down. Oh, no. I thought he's going after $1 million. That's good. So how does, that's the question, right? We want to say whether this Dirichlet integral stays L infinity in time, right? So I put it phi t so that it's easy for me to show some. I don't have to write this, and also you will see it better. So the first inequality I get. I'm sorry, I don't know why I wrote. Leave it as squared. Leave it as, forget the square. I don't need the square. Okay? I'm just trying to see. Let's leave it as phi. We will prove we will prove that for 2D, d phi by dt is less than c phi square. Yeah, we are trying to check our luck on the Millennium Prize problem. And for 3D, we will prove that d phi by dt is less than c phi cube. What is phi 0, by the way? Phi 0 is directly the initial L2 squared. Agreed? So, this only shows that this is, now if I get a bound for phi, it only gives you some upper bound. Even the bound on the right hand side blows up, the solution doesn't have to blow up. So that's the what you need to remember. But now you help me. I'm lazy to go and look at fancy inequalities. So let's crudely think of put an equation and help me solve it. So you will help me solve it. So let's in reality you need to go through Gronow's inequality, but that's a sort of rather very easy step. So if you write d phi by dt is equal to phi c of phi squared, how do you solve this equation? Then you write well, let's do it in this way. I want to write it as phi dot phi, and then I integrate it. This is not how you need to, but you integrate it. So phi t is equal to phi 0 plus 0 to t. I could have left it with an inequality. Put the inequality back. So it is c of phi r times phi r dr. Correct? So far I just integrated it. Correct? And then you apply something called Gronwall's inequality. Gronwall's inequality is nothing but if you just put a lambda here, then you get this exponential lambda of integration, right? Gronwall's inequality. Have you seen Gronwall's inequality? How many of you have seen Gronwall's inequality? If you haven't seen, the point is that it's roughly equating it and integrating and then you're getting right hand side. You need to use some iterative methods, some monotone methods to solve, get the inequality, but it essentially suppose this is some h of r, then what do you get? You get phi of t is less than or equal to phi of 0 exponential 0 to t, this h of r, right? So that is c is there, phi of r dr. So it allows you to write this. Just like the ODE, just that the little trick you keep this guy here. Okay, everybody agree? I should have had h of r dr. It's if you have h of r dr here, it's just exponential integrating factor, and that would have given you this right hand side. So it's an integrating factor. This doesn't look like something. What is this? Professor put here, and there's a phi here. But let's take a look at this term. It is in terms of phi, so let's write it down. So what is this term? If I go and put my notation back, so that term, the term on the numerator of the exponential, is it clear? I put too many lines here. It's a exponential is equal to 0 to t gradient of u dot r. What is here? What's the power? Huh? Go back and look at the definition of phi. Phi is what? Gradient of u squared. And therefore it's squared. Squared dr. right? Now help me. What can you say about the left hand side? Which blackboards are you looking at? That one and that one? There's one more over there. Whiteboard, right? I know you guys were looking at that and looking at that. Yes, I have used this. I have used the definition, I brought it here. And so I concluded that this phi t is sort of a puzzling thing. I have phi again here, but let's talk about that. So what I am trying to conclude is that whether the direct line integral will stay uniformly bounded in time, right? But I am going to use a weaker statement I proved before. What was that weaker statement? Where that weaker statement lies? To my left or to my right?
The supremum that not in L2 is dominated by that.
This guy? No, we don't have that. How about the first one? Look at this guy. What I have proved is that, yeah, it's not uniformly bounded, but what I have proved that it's co-integrable in time. And now look at the numerator, whatever it's called, the exponential argument, and you have exactly that, and this has to be bounded by the initial data, right? Because that's isn't that my energy any L2, right? I haven't taken any smooth initial data here, right? So this is by the energy estimate, this is bounded by dot 0, L2 square, and therefore this side is bounded, and therefore this is bounded. So what I have concluded is that the 2D version of the Millennium Prize problem, for which no $1,000,000 is L infinity in. So what I have, so this type of bootstrapping comes even in conservation laws in many places. Yeah, well, no, if you look at it here, this is initial data, yeah, in order to get to that, this one, yes, the initial data is smooth, but that's not the, this is actually, phi 0, that is a good point, is gradient u dot 0, right, L2 square. So in order to get to this inequality, I will get the smooth initial data. So, so what we have concluded is that with this weaker statement that my entropy is co-integrable in time, I can conclude that entropy is actually L infinity in time, right? Because this tells you that for all t, this guy is finite because this is always finite. Can you see the point? Otherwise we can talk.
So data is also H1.
Yeah, that part is okay. Yeah, we'll keep, when I prove, this is finite, yeah. Instant data, I'm going to give you C infinity.
But you assume the first inequality.
You mean this one? Yeah, I'm going to prove this too.
You will prove.
Yeah, I will prove, for 2D I will prove this, 3D I will prove this. But 2D, I'm just showing that, in both of these cases, we will work with finite, the H1 norm is also finite. I give you smooth initial data. Yeah. So I say the Millennium Prize is not about the smoothness of the initial data. We give you that. Smooth, but so the higher order norms you can assume, but they are finite, but they are not small. That's the point. You can assume any norm to be finite, but they are not small. It's essentially, we intuitively visualize it. If we want this to be small, then the distortion has to be very mild, right? We want the distortion to be very vigorous. So what we have proved is that this weaker statement, that is co-integrable, this given by the energy estimate, we prove that is L infinity in time. Everybody agree? Students agree? Or not agree? So what here we had, I write it in, so that inequality correspond to L2 0t H1 norm, right? Is as a spatial, but we have concluded from here is that if that is so, and if the initial data is in H1, then u is L infinity 0t H1 now, and that's good enough to complete. I claim that, yeah.
Sir, here you are saying that phi of t is bounded because of that L stroke is L2.
Yeah, this inequality.
Stage first go back.
Yeah. Yeah, let him complete the question. What was the, yeah.
From in the inequality, in the energy estimate, we took that L stroke is L2.
Yeah, this is L2 in time. Yeah.
That implies this is bounded.
Yeah, so now we come here. I claim that in 2D I can prove this inequality. I will show you, right? And then we come here and we find that the direct line integral, which I define here for all time, is bounded by this term, and where this exponential appear to, right, is appearing here. But then I know that this is finite, bounded by the initial data, right, for all time. I already proved in the energy estimate, right, and therefore the right hand side is finite for all time as long as I have the initial data is finite as far as this is concerned. In order to keep this finite, I need the H1 in the initial data. Okay? Oh, so then I say that phi supremum t, phi t is finite, right? Yeah, so, so right, supremum of, but what is phi t? Phi t is already positive quantity, is this quantity, right? So it is L infinity in time. So 2 dimension is, if I tell you that initial data is L2, then I have that 2 and 3D. But 3D, if I tell you that the initial data, I give you a little bit more. Initial data is also H1 norm finite. Finite is not a problem, I give you finite in this Millennium Prize problem. Then the Grunwald's inequality, immediately give you this. So we need to get this inequality, but we can prove this, right? Now again, let's go and do what will happen to this guy, right? And then I will show you how to prove this one. That's because I don't want to take you through the proof and then because then it is you know, we are heading through a jungle. You don't know where are we going. Here I show the direction first, and then I will take you. Okay. So everybody have this in mind. So this is why this is so fundamental. All the deepest problems can be stated once you get the energy estimate, and it is true for 2 and 3 dimensions. Now help me solve that second problem. That's where I really need the ODE skills, which I have forgotten all those things. So what can you do with this? Why don't we put equal and then try to solve? Am I okay? Green light to proceed, or right?
Actually, you said phi of r is bounded by the initial data. And for viscosity very small, for example, you said 10 power minus 8. This might be bigger, right, sir? You have to add a constant there before initial data.
Oh, yeah, but you mean the nu? The nu is small. It doesn't help. It doesn't affect this conclusion. Nu is extremely small. That's okay. So then I divide by, right? So it's the same conclusion. So far there's no smallness assumption in any of the data and so forth. Can you help me solve this? So that will be d phi by, let's write equality, forget the fancy inequality. That's what you go and look up when you, because we have inequality. So this is equal to dt. So what is that? That is 1 over phi minus 1 over phi squared, right, when I integrate it, and there is a 203 comes in, I am going to multiply it through. So that is equal to some ct plus d, right? Let's leave it like that. So let's write it this way. The d is a negative is absorbed in. You agree with this integral? In doing this, I pick up a negative I'm lazy to pick up what is this 2 or something, but this one was just t, and therefore I write this as 1 over phi squared, and I write minus ct, and then plus some constant d. Everybody agree? It's just an ODE integration, and therefore phi is equal to 1 over phi of 0, phi of t is equal to 1 over square root of d minus c of t, right? So far I didn't bluff anything. I did a little bit in picking this constant because otherwise it's okay. This sign is necessary. You can actually determine what this guy is. So what is this phi t? Phi t is gradient norm of u of dot t L2 square, and therefore phi of 0 is initial data, right? Gradient of u dot 0 L2 square. So t is equal to 0, 1 over square root of d is that, right? So d is equal to what? 1 over that. So it is in this way you clean it a little bit. Phi is equal to, in this equality, 1 over, I think it looks something like this, 1 over gradient u dot 0 squared minus ct. Is actually there's no, see here there should have been some number, you can put that more correctly. Agree with the sign here? Right? Actually, so if I would have done more carefully, then I would have ended up as an inequality here. This was an inequality, this was an inequality, and this was an inequality, and that was an inequality. Let's leave it like that. So what can you say about the, so the left hand side, I have the direct line integral. This h1 norm I was trying to show that is bounded, right? L infinity. Right hand side, can you plot this function? So when t is equal to 0, it sort of starts like that, right? And actually starts with precisely 2 or 4 at the d must be, I think it should be 4. Why it is 4? Because square root of d is equal to initial data, right? Right, and therefore it's d to the power 4. So initially phi 0, it starts with that initial data, and then what happens to this right hand side? What kind of function it is? Does it stay bounded? Goes to 0? Correct me if there's a, okay?
Sorry, it should not be greater or equal, pt greater or equal than 1 over.
Oh, because I have, yeah, I just went and corrected. My original problem is this one, right? So I skipped some inequalities here. My original problem was this one. I did the equality and I cheated, but right?
No, what he is saying is that 1 over phi squared is less equals to. So
Say the last word I didn't understand.
1 over phi squared
Yeah.
is less equals to, right?
Is it equal to what?
1 over phi squared is less or equals to that thing. So
Yeah.
minus equals. So when you
Greater or equal, right?
Equality sign.
Oh, this would be greater or equal to.
Exactly. pt greater or
Instead
equal
of less or
than
equal to this.
Yeah. So
Only t should be greater than.
yeah, but I multiply by multiplied by minus anyway. There was a minus, so I multiplied. So then this should have been the other inequality, the other sign, right? The other side, because I multiplied by minus after integration, and then I get this one, right? I know this is right. Good observation. Okay, so what is happening to this term? This is don't worry about this one. This is says that this is some thing we ended up. I think 4 is correct. Why? Because t equal to 0, 1 over square root of d is equal to directly norm squared, and therefore d is right. to the power 4. Okay. So at t equal to 0, you start with phi is what? The Dirichlet norms initial square. What is happening to this right hand side? It doesn't say anything about the solution, but we just got a bound on the right hand side, right? You don't have to worry. What is this side? This is some constant. I have integrated in space, so some constant. What kind of function is this? Will it? What will happen when t is equal to this side? This is equal to 0. What will happen? It blows up. Yeah. So it goes. So you do pick up a t star is equal to what? T star is equal to so 1 over some c times Dirichlet norm initial data to the power 4, right? Correct? So you pick up a t star which is actually 1 divided by 4th power of the Dirichlet integral, right? Now let's talk about again physical intuition. If the initial flow field is very turbulent, right? You're taking a river which is aggressively flowing. So the distortion is very high, and therefore the Dirichlet norm which is obtained by taking gradient is large, right? Because that's what Dirichlet norm is taking the derivative. So is there a lot of velocity variations, the H1 interior norm is large, right? These are not useless functional analytic aspects, you have to think physically, right? So the u squared is the energy. The first integral signifies, it says something about the derivatives. And so initially if the distortion is very high, then this term is large. So what happens to t star? T star will be large or small? I'll tell you this way. Look at the river in very passive time. So not much turbulence you see. So the initial this guy is small. And now look at the river in the monsoon time is very vigorous. So the initial data is high. Then H1 norm, right, is large. What happened to T star when the initial H1 norm is large? It becomes smaller, right? So this is why you can see that as the initial data has higher and higher turbulence, distortion, your blow up time of the right hand side, it blows up even sooner and sooner, right? So that's this is an upper bound. This is what Professor Bartos taught us, where he wanted to test it numerically and see whether this saturates. In fact, this is the best thing you get, or maybe because this doesn't mean the left hand side should also blow up. It can actually do this, right? Because it doesn't say anything about the solution. It just says that it says below the value. So what is the story? Say in 2D, if you accept these two estimates, then in 2D we managed to prove that the H1 norm stays finite for all time. In 3D, it can possibly blow up in a finite time determined by the initial size of the H1 norm of the initial data, right? Right. So this is what the current situation is. There is not better than this. After almost 100 years, this little estimate we did is just about the best we can do. So if you turn chapter 5, Roger Timam proves. So I will show the estimate, but I will now talk a little bit about chapter 5 here. And in particular state the theorem that he has, so that you can go and read. With this result we have now, you can believe it or not, you can understand the Leray singularity. So, and you will find that because it's proven essentially state at the bottom, and it's proven right here this much, and good deal of it is just these things. So, and it's a big results. So what these inequalities try to tell you is that, okay, if this initial data is L2, then I have this. Initial data has more smoothness, H1. 2D, yeah, then the H1 norm also stays bounded, but 3D you don't have. You can try to do better, there's nothing you can do. You will say maybe something to know with the Navier-Stokes equation. How about taking the curl and take the vorticity equation and try to prove? And you will run into trouble immediately in the first step. Then you try to take the L2 norm. So it's nothing to just because, not because we don't understand the Navier-Stokes equation, or what we engineers know, we don't know. We know all that. So, so it is here. So Leray noticed this one. Then he proved that, okay, so maybe if it does this blow up, but remember that doesn't look very good, because what the right hand side says is that the H1 norm blows up in finite time, and maybe it stays blown up. Can that be possible? So I realized that I didn't prove these things, but it's easy to prove that. But that's easy inequality. But so we managed to get, I write it in an even bigger. So what we have gotten, this phi t, gradient u dot t L2 squared is less than or equal to 1 over square root of, there may be these c's missing, but 1 over gradient u dot 0 L2 to the power 4 minus some constant times t. Maybe they are not, so this is what we have proved, right? And we agree that the right hand side, if you start with here, it blows up. But let's say your interest is up to some finite time, this is the T star. If the right hand side is right, if this is the sort of things is trying to do, let's say your solution also maybe blows up, go to infinity, and stays infinity here, right? Stays infinity in a finite time. Is it possible? Because that's the question Leray asked. That's called the time singularity, right? What is the singular set? In the times, he says if it blows up, right?
Repeat the question, sir.
Yeah. So what the right hand side appear to tell you is that the vorticity content, right, which is the H1, this H1 norm, can potentially blow up because this entropy, because this right hand side blows up. So my question is, let's say that blows up. In fact, goes to infinity. Can it stay in infinity for a certain finite time?
The last chapter, it blows up in a small set where the turbulence is located. So it's possible.
Yes, physical argument. Yeah, but we don't know, right? So that's exactly the question. Whether it's we don't know. That was sort of a conjecture that it maybe blows up and stays infinity, so you cannot define, it's so intense. In fact, if you look at some of the tornadoes, right, you have maybe a region where integral of the gradient may be very large and close to infinity. So the question is, can it stay, this norm, can it stay as infinity? Let's say it blows up, right? Can it stay at the infinite value for a set of positive measure? That's more in time.
Then the first equation will be in trouble.
Yeah, good, very good. So this equation in trouble is one way of saying that. That equation doesn't permit you to do that. Why?
Because it's bounded by that finite thing. This side then will be infinite. We have positive measure infinite.
Yeah, very good. If it's let's say even in a little interval, if this one stays infinity, in that interval, the contribution to the integral will be infinite, right? Since that cannot happen, this singularity, if it happens, it should be in a set of measure 0.
Asymptotically maybe.
Yeah, so yeah, it can go asymptotically to the end, to any time, right? We don't know, right?
It may never touch also. We don't know that also.
Yeah, so it cannot asymptotically increase to infinity because this won't be then finite, right? You cannot have a function which even goes to a finite value in a positive measure, because then the infinite time contribution will be infinity. So what this says, everybody understood that point. In order for this to make sense, this has to be finite almost everywhere, right? If it is non-zero in infinity in interval, any exotic interval, but of finite measure, then this will be infinity. So those are the two informations you have. This says that okay, it's only zero in a set of measures, zero, but then that looks like a very nice result. In fact, if you only look at this one, it looks like it looks like all you need to prove is something. So it looks like the $1 million prize is right there. So then you try to say, okay, that's what we try to do here. So we say this looks like it's quite integrable in time, so it's almost finite. So all we have to take is to take a H1 data and then try to show that it's uniformly bounded, and we run into trouble here, right? So then you ask the time singular set. In this, what can you say about the sets where this actually blows up? Because this seems to indicate that it blows up, right? So I will give you the time singularity results, and it's to prove essentially it's based on this one. The Hausdorff dimension is proven by covering the time singular sets by these balls, and then you define Hausdorff measure. It's very intuitive, even if you are a more applied person. I just write down the results so that then I can go and show the theorem. So this is theorem 5.1. To clarify the notation, the space V is taken, which you have already seen it several times, is H1 0 omega, divergence of U equal to 0, okay? Because this is more, I spoke in terms of H1, but it's actually zero boundary and divergence free, because that's the appropriate space. So the statement, originally due to Leray, it was being polished, is that for omega in R3, it's actually like that. It's all space of R3. Let U be a weak solution to Navier-Stokes equation. So the weak solution is that you just use that those two inequality alone and prove existence. So let U be a weak solution to Navier-Stokes. Then there exists a closed set, which he denotes by E in the interval 0 to t, whose Hausdorff, whose half-dimensional Hausdorff measure vanishes, and U is at least, can you read in the last line if I write here? At least continuous from 0 t not in E into V. So if you read about Hausdorff measure, Hausdorff dimension, Hausdorff measure is something like that. It is infinity and then it becomes 0. So this is the point. That's why you say half-dimensional Hausdorff measure vanishes, because you are looking for the smallest dimension. What does this say? Outside this some singular set in the time interval, right? U is actually, as an h-value function, is even continuous and nice. L infinity continuous and nice, right? So, so Leray was interested in getting a finer answer about this this inequality. He says that okay, this immediately says that well, almost this only can go to infinity in a set of measure 0, and then that gives you that singular set is called the time singularity is of whose Hausdorff half-dimensional Hausdorff measure vanishes. The other one is called the space-time singularity. That's a little bit more involved, maybe a lot more involved. That is to just look at xt plane, and you know, you want to say okay, all these H1 you know, these Sobolev spaces were. You just tell me whether the solution is well behaved in space-time. So the results is by Caffarelli, Kohn and Nirenberg, the best results. Here he proves the same results, a weaker version of it, is that the singular set in space-time is so small that it says one-dimensional Hausdorff measure vanishes. Here they prove that it's I think 3/2 or 5/2 dimensional. So that was.
So if suppose half-dimensional measure vanishes, does that mean one-dimensional will also vanish?
If it is, I think if any other height, yeah, that's essentially like this. The dimension is like that. So it's anything bigger than that is also 0. So it's the smallest dimension for which the Hausdorff measure vanishes.
So actually the subset of measure 0 of the interval 0 t. Is that the thing?
Yeah, it's a way of characterizing. It's another measure which known to be more refined than Lebesgue measure. That is the point. Okay. Okay, good. So now I have half an hour. We will prove these two. This is right. So you are probably surprised that all these big results by big mathematicians are just all here. It's not a very sophisticated calculation. It's just that in a way of understanding more deeply and right, taking a closer examination. It's a very good examination observation you made, saying that okay, this the fact that this cannot blow up in a set of positive measure is already in here, even for 3D. So you can see that the Millennium Prize problem is not so bad, it looks like, right? Because I only wanted to say that this is L infinity, but it looks like is mostly L infinity. That's what that result says, right? Okay, so now how do you prove? How to prove these things is a nice exercise in and well-known exercise in with these Navier-Stokes things. So we will prove. So I'll prove these results and that results. And that's good enough because I wanted to sort of take you a little bit deep into Navier-Stokes in some of the compelling areas and see so that you will start reading, and to show that it doesn't involve fancy mathematics. The best results in Navier-Stokes doesn't involve any fancy mathematics. So first we will keep these guys because that's we need this. So to take the H1 norm, you know, just like you multiplied by u, next time you want to multiply by something that looks like a Laplacian, but if you multiply by a Laplacian, you are in trouble because the pressure term doesn't go away. The trick actually goes back to Giuliano-Prodi. You say the first name right? I think Giovanni or Giuliano Prodi, G. Prodi. He has an Italian. Giovanni Prodi. Prodi, I should write, such a big mathematician. He sort of disappeared in the. Most people cannot, these days cannot point to him, but it was Lyons and Prodi in 1959 who said that in 2D, within these inequalities, you can prove uniqueness, right? Maybe that uniqueness I had to do it in one of the other lectures. So it was Prodi, but Prodi also noticed that the eigenfunctions of the Stokes operators are very useful in taking high order a priori estimates. Otherwise you have all these nasty terms involving pressures because the Laplacian, it doesn't vanish on the boundary. Even the velocity vanish on the boundary. The Laplacian doesn't vanish on the boundary. It may be divergence free, so it doesn't belong to the fractional powers of you run into all kind of problems. So he said work with the eigenfunctions of the Stokes operator. the modern interpretation of that is the either work with A or fractional powers of AU, AA. That's the modern sort of language. So it's sort of this idea came from Prodi, but he's disappeared in the scene. Anyway, so if we go back and write down the what is called the abstract form of the Navier-Stokes equation is equal to, let's say, U naught. So I go back and write down now. I want the function spaces so that these manipulations are easy. So I write U dot belongs to L2 omega, div of U is equal to 0, and U dot n d omega is equal to 0, and the space V, I take it as U belongs to H1 0 omega. So this time the full boundary is taken here, and div of U is equal to 0. And then I mentioned about the Catabrija regularity theorem, which tells you how does the domain look like. So that is the domain of A is equal to simply H2 omega intersection V, and domain of A alpha, the simplest setting is H2 alpha omega intersection V for alpha, in between these two. In particular, you can actually for LP and so forth, we can very finely characterize this, but this is good enough for this calculation. And we define what's called the Helmholtz projection. It is fashionable to say that it's Helmholtz and Hodge, but Hodge's work is essentially taking Helmholtz and into more general differential forms and so forth. But so it's Helmholtz projection, which is PH, takes you any L2 space into H. What happens is the L2 space, so any element U, I don't know why I write it, yeah, if you can allow me to write this one, this is origin, this is some U. So there's a projection here V, that's the divergence free part, and that is the gradient. So any U in L2 omega, you can write it as U is equal to V plus gradient phi. It's the Helmholtz decomposition. With appropriate Sobolev spaces, where V actually belongs to H. So this is any old U, but then that can be decomposed into an element that belongs to this nice space, this one, divergence free and parallel to boundary, and the other one is just gradient. So this projection P, PH, actually takes any U and gives you V. So this one will be divergence free and V dot n is 0. So you have these extra attributes. Take any divergence free function, it's so that's this projection. Why do we need this? Because then the Navier-Stokes in the classical form, by simply applying the projection, it's converted to this way. Another way to see that is you just write it in a weak form, multiply by, take an element from this one of these spaces, nice spaces, and take inner product with the divergent Navier-Stokes. That already killed the pressure. So what is left on the left hand side is actually now an element in the Hilbert space, and that is this one. Okay. So having defined this one, my terms look like this. So AU is nothing but minus Laplace U for U belong to domain of A. I have defined what is domain of A explicitly, right? I have domain of A is all elements coming in this intersection, or you can all elements that come from here and fall back into L2. And PU, P of and B of U is this, I missed, so minus PH, and it is PH U dot gradient U. So, how did we get energy estimate before? I multiplied this by, just took inner product with U. This time I will take following Prodi inner product with AU. So that's the point. We are going to get the H1 estimate. There is results I should have put. It's easy to show that the norm of V is actually the norm of A half U in the L2 norm. This key thing we want to use, because V is actually like the H1 space. H1 space is almost like the half operator. Okay, so get rid of this so that I can estimate. I think I can even prove 2 and 3 D uniqueness also, depending on how the things go. So let me write this one a little bit more fancy way. This is now nothing but, well, I shouldn't say nothing but, because it's non-trivial to actually understand that, particularly in unbounded domain. But it is A half U of dot. Okay. Why it is like? Because H1 norm is like taking derivative. Laplacian is second derivative, so square root of Laplacian is like the first derivative, gradient. So this is then A half U. So that's the only to phrase it more abstractly here, so that we can work with this. Everybody is comfortable with that, right? Second derivative is like Laplacian. Okay, so now we take inner product with AU. Okay, so that whole thing is taken inner product, Hilbert space, inner product, and I will set that to 0. So the first guy look like what? You go back to the integral, it looks like, so I want to write this as, it says d by dt half A half U squared. I need to convince you that that is in fact, this is in fact that. So, so how do you see that? It says, so write d by dt half A half U H norm squared, right, which I have there, H norm. If I don't say anything, it is H norm. It is equal to half d by dt A half U, A half U. A being self-adjoint, all its powers are self-adjoint, so move it to one side. So if I move it, it says half d by dt U AU, right? And therefore, now I go in, and these are spatial business. I go in and differentiate by parts. I first get du by dt times AU, then I will get u times, which I will write here, otherwise du by dt AU. The second one is half u times d by dt of AU. I am going to take the d by dt inside, so A times du by dt. This is formal, but we are dealing with a priori estimates, and that is exactly what you have here. Just leave it like d by dt of AU. Okay, because if you move this A this side, that's what you have here. So the first term is this one. Everybody is comfortable with that? Or you didn't like it? Didn't like it. I can see it. This much is okay? This much is okay? Now let's differentiate it. So if you differentiate it, half, think of this as some matrix, so I just go in and differentiate it. So it is ut au. And then I differentiate the other one, so that is half u aut. Now only move half to, so that's what I have here, right? That's what I have here. And therefore that's equal to the left hand side, right? This part I am going to let you try it yourself. What can you say about this term? That term is plus nu of au squared, right? This is au in a product with au, that's nu of au squared. And the third term I will write as b of u and au, so that the whole thing is equal to 0. Okay, so I don't think I need to explain that one more time. So the more I try, I'm going to go downhill. So go and sort it out. Anyway, so I end up with this one. Now I want to estimate this nonlinear term. This is the trilinear form we introduced a number of times. So that looks like. So the trilinear form, we wrote it as u dot gradient u dot au dx. It is okay to write this way because it's inside the integral. So the trick is that last time I didn't have to worry about this term, because last time this term was 0, right? This time it is not 0, right? And so we want to somehow estimate in a way so that to utilize this term, right? This is the difficulty, all this we can't do with the Euler equation. So that's a whole different story. So I want to estimate this one so that when I somehow split and write, I should be able to use this guy to maybe cancel half of some of the bad terms appearing on the right hand side. So now we start with 2D. So 2D, I am going to write u au. So that is estimated as u of L4 gradient u of L4 and au of L2. Can I do this? Why this is correct? Is 1 over 4 plus 1 over 4 plus half is equal to 1. Okay? Why I didn't use higher power of this guy? I had to be careful I don't introduce any derivatives on this one, because it's already the Laplacian, right? And now we use what's called the Gagliardo-Nirenberg inequality. Is that the trick? Do I need to use it or just... Yeah, it's used. So Gagliardo-Nirenberg. This is also so the Gagliardo-Nirenberg inequality is that u of it's called the Ledzinski inequality, but now it is Gagliardo-Nirenberg. I think it's also in Leray. It's a good exercise for you to go and see whether this is already in Leray. How do you see it? The Leray's papers are posted, so you should be able to find out. So it is L4 norm is bounded by some constant which is actually independent of the size of the domain. So it's applicable in bounded as well as unbounded domain, and it is u of L2 half gradient of u of L2 half. This is for 2D. For 3D, it looks like this: u of L4, see, u of L2 1/4, and gradient of u L2 3/4. I will have one more version in a moment. By the way, if anybody lost here, that's not where the life is. It's just a trivial step. Okay, if you don't like that, you can always write du by dt times Laplace u dx, and then try to split one of the derivatives to the other side. So you will end up with this one. My goal is now is how can I estimate this nonlinearity? I am going to bring it to the right hand side. So it is going to be like this. How can I estimate so that I don't run into, when I try to get bound this norm and that norm, I don't run into some higher order power. The closure problem I shouldn't run into, right? Otherwise then I go endlessly. So the same trick we used before. So can we use the earlier estimates so that your life stops here? So we use Gagliardo-Nirenberg to this guy and also to this, because these are L4 norms. So this will look like, so this is 2D. This will look like u of L2. I won't write L2 because if I don't write it is just L2. Agreed? So it is half and it is gradient u. So I am just using for this one this estimate, right? So it's gradient u. Help me with that. What power? 1/2, because I am only writing for this guy. The other term, so this one I apply, that's where there's a trick actually, so one has to be a little bit more careful. I'm going to write, so this one also you are going to use the same one, right? Just that, so here you will have, if I apply Gagliardo-Nirenberg for this one, I'll get gradient u half, right? Because that's what this says. But this becomes gradient of the gradient, so it looks like Laplacian, but the correct one is A. So you had to be careful. There are things you need to worry about. In order to actually correctly do that, you need to run back to the Catabrija regularity theorem, which says you that H2 norm and the domain of A. You know, if you, the moment you prove regularity theorem, AU L2 is equivalent to U of H2. That's the Catabrija regularity theorem tells you. Otherwise, you are in trouble here because you are trying to generate a Laplacian here, but so you want to put AU back. So these are looks like trivial steps. It took a lot of many years to people to figure that out. So what I have, if I replace this by gradient u, I have gradient u, but here gradient of gradient u, so roughly it's Laplacian u, but Laplacian u is bounded by, is equivalent to the AU norm by the regularity theorem, right? That's the domain, and therefore I can replace that by AU, right? So the next term, so this is gradient u half and AU half, this one, because that's this term, right? This term half and half. And then I have this guy, so we just write it here. Or make this one 3/2. Everybody agree? Question?
The norms are L2
Yeah, all the norms are L2, right? That point you will not be able to figure it out yourself if you don't understand it from, right? Because the domain, the moment you prove a regularity theorem, it tells you, because the graph norm of A, which is u times AU, is equivalent to whatever the regularity norm you proved. That's that statement, right? So that allows you, and then this is bigger than the Laplacian of u, and therefore you can write it this way. So this is this gave you these two. This gave you this and a half of that, and I have another one, so I wrote it 3/2. Okay, but that still looks pretty scary. What do you have on the left hand side? I have a square here, and I have on the right hand side I have a u of half, a gradient u of half, AU of 3 by 2.
Power 1.
Just gradient u, because two of these guys. Okay, let's get rid of this one now. So we are still in 2 dimension. So what do you suggest? Not the ones who have worked in the subject before, but the ones who haven't worked in the subject. So what do you suggest? Right hand side, look at the terms. You know, the point is somehow we get to this ground walls inequality like level for a half, right? This gradient norm. But you have all this mess on the right hand side. So what can you possibly do is to use the left hand side. This again, this trick fails for Euler equation because you don't have that term. Remember, Euler equation you don't have that term, so H1 norm, if you get it, you win a Fields medal. So you don't have it. So what you do, you want to somehow utilize this one, and we have this guy, so we will try to force this to take a power 2. That's this Young's inequality business, right? That is, you know, x, y is less than, you know, you can throw you on inequality. So I'm going to make this one 4 by 3. That means I have to make this one by 4th power, right? Because 1 over 4 plus 3 over 4 is equal to 1, right? The inequality I am trying to do is xy is less than or equal to c x to the power p plus I don't know y to the power q d, where 1 over p plus 1 over q is equal to 1. So that's Holder's inequality. Young's inequality. Holder's is with the product. Right, just like the triangular inequality, now you can write it with other powers. So the other power is taken such that this will become a square, so that I can cancel with this. So the right hand side I will make it so that maybe I will make it nu by 2 au squared plus some c which is a function of nu times 4th power of this one. This one is, you know, if you take 4 by 3, it is precisely will produce a square here. So I will make that one 4th power, so that is u L2 norm, how many is square, and then gradient u, or maybe you know, gradient u, or you can write it as a half u to the power 4. So this looks a bit like you know, that I brought some of the things to the right, exponential and so forth. Anyway, so the goal of writing this one is that now I can use cancel this nasty right hand term with half of this one. That looks like Dasaratha and Rama, you know, you give half. So you gave half of this guy in eliminating that nasty term on the right hand side. Agreed? Right? So why did I put over 1/2? 4th power. Because this is gradient. This is a half. This is a half u. So I want 4th power of this one and 4/3 power of this one. 4th power of this one is this is gradient of u. So this side is gone. So you ended up, and I also dropped the left hand, this guy. We can actually get an integral for this one if you want to go higher order estimate. But for the moment, I also dropped this one and introduced my favorite phi. What was phi? Phi t is equal to a half ut squared, right? Isn't that how I defined with a gradient? So this is d phi by dt. So half of, forget the half. So it is d phi by dt is less than or equal to, let's write it this way. Write it as square and a half u squared. And I am going to write this one as maybe some theta t. So I ended up with theta t phi t. Agree? I just split this one into, it was a 4th power, I split it into 2. So that this one I use it as theta t, the rest is actually phi t, I have defined it. So I will end up with, so all I did was I multiplied by au manipulated this guy. So now you apply Grunwald's. Question. Stop me or don't mumble. Ask question. Agreed or not agreed? Right. So apply Grunwald's. So you end up with phi t less than phi 0 exponential 0 to t theta of r dr. Okay. So this is the 2D estimate. So this side is finite provided this guy is finite, right? So what is that guy? Theta naught 0 to t theta r dr is equal to some constant times 0 to t. You write it out, it is u of r L2 norm squared and gradient, or maybe a half u r L2 norm squared dr. This is what I have, right? Because that's what I defined here. Is this finite? If it is finite, then the 2D case is nice. If it is finite, where are you looking at? Yeah, now you are looking at Kasi. So you look at the Darishan. So this is the place where you should be looking at. Can you tell me that by looking at this should be finite? Why it is finite? Does this look like the energy estimate? What do you have here? I have the L2 norm and the Dirichlet norm, right? Dirichlet integral gradient u. Is that what you have there? This one?
Sir, that norm u, now we can dominate it by the supernorm.
Yeah, because this is uniformly bounded. You guys noted correctly. This guy, notice this one. This tells you that this term is uniformly bounded, so you can pull this out of the integral, right? And in fact, it's bounded by the initial data, initial norm. So I even move the integral outside like this, 0 to t, and replace this by the initial data, right? Because it's dominated, that's the second inequality. And this is the energy inequality, again dominated by the initial data, right? And therefore, 2D picture is complete. We proved the 2D picture very nicely. Let's look at the 3D picture. It's very interesting to look at the 3D picture. And the uniqueness is proven more or less along the same line for 2D. And the 3D, can I erase this or can I erase that? Erase everything. So I'm not going to use the Gagliardo-Nirenberg because I was not this version, because this notice that what is happening from 2 to 3 is that the Dirichlet integral getting a higher power, so you are going to get a nastier situation. Leave the Gagliardo-Nirenberg there. Okay, so you remember we came to this position. This much is rather standard, rather straightforward. A half u squared plus nu au squared is equal to minus b u and au, right? Is taken by taking a product with au. Now 3D is a problem. You don't have this nice one which allowed you this subtle way of completing the picture using the energy inequality. So, let's do the following trick. So, I'm going to use B, U, U and AU bounded by U of L6, gradient U of L3 and AU. What should be the power of AU then? If it is 1 over 6 plus 1 over 3 then what should be the last power? This is half, right? So this is half is equal to 1, right? So this is simply L2. The point is to don't introduce too high power here. In your functional analysis class, you studied Sobolev embedding theorem. You have?
This semester only we have.
You are going to study it. Sobolev embedding theorem tells you that well, if pardon? Professor Adimukti did that. Yeah, but you know, we will. So it's okay. We won't hold you. It's difficult. These are subtle theorems, and the bounded or unbounded. If you get a Dirichlet norm finite, this gradient norm finite, if it is 2 dimension, you don't have anything. Unbounded domain. Bounded domain you have, yeah, but depending on whether it's a Poincare domain or what not. 2 dimension, not a Poincare domain, you have don't have any. But 3D, you have this one brilliant Sobolev embedding that tells you that if U of L6, C gradient U. This is proven by Ledzenskaya. Omega in R3, not necessarily bounded or unbounded, but it tells you that if it's you know, Dirichlet integral is finite, so this is L2, then the L6 norm is finite. The highlight of this only seen in the Navier-Stokes in exterior domains usually. So we have that. You know, so this is A half now, right? I'll show you how quickly we can finish the picture. And Gagliardo-Nirenberg, yeah, the 3D is this is, but this is not what I want because it's not going to give me. So I'm going to start with L3. If it is L3 for 3 dimension, it turns out that it gives you half. And it's give you half. So it looks, the right hand side looks identical to the 2D case, provided you work with L3, right? That's also Gagliardo-Nirenberg. You can actually check. And therefore, now we are in good shape because now I picked L3, remember? That's why I picked L3. So now we go and estimate the right hand side. So the right hand side, this is dominated by the Dirichlet integral. So the first term is C times A half U, L2, correct, right? And this one, I can use something that looks like the Gagliardo-Nirenberg, so that is U half, not U, it is what gradient U, right? So it is A half, U half, and then gradient of the gradient, right? That is this one. So A of U. So this part is in applying Gagliardo-Nirenberg to this guy, right? That gives you the L2 norm half, which becomes A half norm half, and gradient of the gradient, which is Laplacian. And now I have one more A, so that I have this guy. So I have this is half. This is half, right? Right. So this is in applying Gagliardo-Nirenberg, and then I have one more A. Correct? So that is the right hand side is and therefore it's less than or equal to C A half norm 3/2 and AU 3/2. Correct? Now, so that's what you have on the left hand side, right hand side, left hand side you have. So now you force it to become again square here. So by taking